All right, so maybe we should have a quiz.
Useless things in iOS 8. It's a good quiz.
I don't want to have to grade another quiz. Just as a review before we talk about how do we compare strings. Last class, we were looking at the equivalence operator, the double equal sign, and how that works with strings. So we created a few strings. And remember, I was saying that every single object you ever create, you always use the new keyword, right? And then we kind of threw the punchline in there. Unless it's strings, you don't have to use the new keyword. But we kind of saw the effects of whether or not you use the new keyword with strings. Now, having said this, I'll tell you, you will very rarely, if ever, create strings like this. You will almost always create strings this way. Because the correct thing to do is not to compare strings using the double equal sign. All right, we'll talk about that here in a few minutes. But just to review here, we created two separate strings here, S and S2, using the new keyword. And what's our new keyword? If we were to have a quiz, I might have asked the question, tell me what the new keyword is and why do we need it? What is the new keyword? Besides the word new.
It stores it in a new location.
Stores it in a new location. Okay, tell me more about that.
Both have different addresses.
Okay. I referred to the new keyword as something, your hair's still wet. Real estate agent. Okay, what do real estate agents do in real life? Find us a place to build our house, right? Or find a house that's already built. But in our example here, a real estate agent finds us a plot of land that we can go and build a house. Same thing's true in our programming languages. The new keywords, our real estate agent goes out and finds a spot in memory where we can store a variable and returns for us what? Memory address, right? Okay. What's a primitive type variable capable of holding a memory address called? Talked about this a little bit last time. Java doesn't actually have them, but the language that Java came from, C and C++, supports them. Pointers. Okay, so we have this idea of something called a pointer, and a pointer is a primitive type variable capable of holding a memory address. And the reason why they're called pointers is because the value stored in a pointer primitive type is a memory address, and it points to the actual value that's stored in memory. That's why it's called a pointer. Okay, so the memory address points to a place in memory. It references a place in memory. And that place in memory is where the actual value is stored. Make sense? Okay, we'll talk more about pointers in here. More from we kind of looked at the example yesterday. We were last class when we were printing out a bunch of different objects. And we saw some of them look like crazy memory addresses, but some of them looked pretty. Like when we printed out when we used the system.out.println method to print out strings. It looked good. It looked like the string. But when we used system.out.println to print out, we created an instance of the random object, which we don't know much about, but we just know it's another object. It looked like a crazy memory address. Why is that? Why did random look one way and strings looked kind of correct, like what we would have expected? There's an underlying feature that the println method knows about, and it takes advantage of. What was that? Oh, another good quiz question. Just as a quick review here, I'll create a random r is equal to new random. So I'm creating a variable name r of type random, and I'm using the real estate agent to create it. Okay, remember this guy's called, what's this guy called? Similar to this guy? Constructor. That's the dude who's building the object for us. Okay, we don't know how to write them yet, but we know that they exist. Okay? So this guy actually does the building. This guy tells them where to build it. Ultimately, the value that gets returned here is a memory address where the house was built, where the object was actually built, so that when we use it, it can resolve to that memory address and we can ultimately get the value at that memory address. So if I tell you to come to my house for a party, I'm going to give you my address. You will travel to my house, and then you'll be at the house. looking at the actual object. Make sense? Okay, so that's kind of how pointers work. Now, if I go in here and I print out, let me just comment out that other print statement up there so it doesn't confuse things. So I'm going to print out R. We're going to see the memory addressy looking thing of R. And the reason why it's somewhat pretty printed where it says java.util.random is what? Why does it look a little bit formatted instead of just a strict crazy memory address?
Inside Java virtual machine.
Yeah, Java runs in a virtual machine. So the Java virtual machine actually virtualizes memory. So you have real memory that sits at the top. Then you have the virtual machine, which is a program that runs in real memory. Okay? And that virtual machine is going to block off a chunk of real memory so that it can manage it internally. So when the new keyword in Java looks for a memory location, it's talking to the Java virtual machine, asking about its free memory, which then manages real memory. Okay? So this is a Java-esque memory address, if you will. Okay? But this is the part of it that kind of looks memory addressy. That's a hexadecimal value, a base 16 value. All right? So random objects look like that. But if I were to print out one of our strings, even the one using the new keyword, like S up here, which was built using the new keyword, just like R was. So we know the new keyword is a real estate agent that ultimately uses this guy to construct our string and returns a memory address. When we print out S, it's going to print out hello, not a memory address. Why is that?
The memory address is holding the value of hello.
Well, the memory address is holding the value of our random object as well. And the memory address isn't holding the value of the hello. The memory address is holding an object of type string, which happens to hold the value hello. Just like our random object is holding the value of R, which is an instance of our random object, which holds some value, whatever that is. Because remember when we talked about objects last time, we said objects can store 0 or more values and potentially do more. It's our ability to create our own variables. We haven't created a variable yet, now we're just starting to use objects, but you can create your own variables. But why does one of these guys print out crazy memory address and the other one prints out something that seems to be more appropriate for strings? Certainly it seems like strings have done something special, correct? Over and above that. We talked about that last time. What is the special thing that strings have done? Two-string. So something we don't see here is each of these guys are calling their two-string method. Oh, not that one. Okay, each of these guys are calling their two-string method. The println method has a whole bunch of different versions. One version knows how to print out bytes and shorts and ints and longs, and there's another version that knows how to print out floats, so on and so forth. There's also a version of it that knows how to print out objects. Okay, so whenever we pass it something of object type, it automatically calls that object's two-string method. Okay, we don't see it, but we know that's what's actually happening under the hood. Whatever we passed in here, if we just passed in the R, it's going to take that object and call that object's two-string method and ultimately display that. That make sense? Okay. Now, when we actually look at the documentation, you'll actually see that there's a version of println that also knows how to print out strings. So you actually take this step one step further, but pretend like that doesn't exist right now so I can explain this concept to you. All right, so it's automatically calling the two-string method of whatever we put in there if it's an object. Now, random's two-string method happens to boil down to crazy memory address. S's, our string's two-string method, boils down to a nice, pretty string. But we see the same output we had before. So, kind of proving that two-string was there, but invisible to us. Okay? Why are these two different? Random gets its two-string method from who? There exists a hierarchy in the object model in Java. At the very top of that hierarchy, we have a generic object type called object. And that generic object type has a minimalistic set of features that all objects must share. And one of those features is this method called toString. And that's why println can write itself in the way that it writes itself, such that it can always call the toString method. It knows that every single object will have that method. Okay? Because it came from the great-great-great-great-grandparent of every single object. Top of the hierarchy, generic object. Okay? Now, generic objects have to write all of its features in the most generic way possible. And since we talk about everything having to be stored somewhere in memory, and we said that every single object is built using the new keyword, except strings, but every single object is built using the new keyword, we know that every single object has to be stored somewhere in memory. We actually know that every variable ultimately has to be stored in memory, but objects are working with pointers. Okay, they're working with memory addresses specifically. So perhaps we can say that for an object, the most appropriate generic version of what toString should do is boiled down to the pseudo memory address in the Java virtual machine where that object lives. That might be the most generic thing that makes sense. Kind of get that? They had to make a choice. The people who wrote the Sun Microsystems people now from Oracle, because Oracle bought Sun Microsystems, the people who wrote Java, they had to make a decision when they wrote the language. What goes into the generic object type, and what does the toString method do? And they just decided, let's return a string representation of the memory address. Okay? Well, the random class chose to just accept that generic version of that method. They didn't do anything special over and above that. Make sense? But now a string chose to rewrite that method. Rather than just inherit from its parent, or grandparent, however far up the ladder it has to go, the toString method from the original. Rather than inherit that and just do the generic print the memory address, strings chose to rewrite that. It's called overriding a method. They wrote a more local version of the method. And just like variables resolve to their most local definition, right? Methods also resolve to their most local definition. So if we're dealing with a string, and we call that string's toString method, it's going to first look inside the string class and say, is there a toString method here? If not, go up to my parent. If it's not there, go to his parent. If it's not there, go to his parent until we finally get up to object. If it's not there, then we throw an error. Okay, but we know that object has a toString. Okay, because I told you it does. All right? So the string class, whoever wrote that, specifically created a newer version, a more local version of the toString method that does something a little bit more appropriate for strings. Just return the contents of the string. That make sense? All right. So a lot of really important under the hood information in that discussion. Okay, things that it's important that you know, but it's kind of like we think about this like driving a car. Most of us in here can drive. We drive cars, and do you have to know how it works under the hood in order to drive a car? You don't have to know how an engine works and stuff like that, correct? You can still drive it. So realistically, you can still program without understanding these concepts. But as computer scientists, we really want to understand these concepts because understanding how things work under the hood gives us the ability to use other features of the language because we can kind of make a pretty good and educated guess on how they likely function, as opposed to just memorizing the concept that, oh, when I print strings, they look right. When I print random objects, they don't. Okay? You could just commit that to memory and just have a whole list of different objects and how they might look when you call the method, right? You know how println works. But knowing that println is actually calling this toString method allows you to use the documentation, the Java documentation, to understand how objects work. So something I'm going to really harp on in here is being able to read the documentation. All right? So something that I'm not a big fan of outside of kind of some structural stuff. Like, for instance, I asked you all to memorize the Hello World program, right? Because that's the structure that you'll start with for every single program you'll ever write. It's important, okay? But When you get out of here, you get your degree and you go get a job as a programmer, is the boss going to lock you in a room and just say, look, if it's not in your memory, I'm going to fire you? You're going to have reference books, right? Okay. Programming is a skill set, not something that you've memorized. There are going to be aspects of the language that you will have memorized over time just by accident. Okay, I've been writing Java programs since the day Java was invented. I don't know the whole language. I've probably only used, the language is huge. I've probably only used, I'm going to be generous to myself and say 20% of the language. I bet you it's actually less than that. There's a zillion things the language has built into it. It's a general purpose language for solving a whole bunch of different problems. And I've only used the parts of it for the problems that I've happened to solve. Make sense? So I've been exposed to Java for years. 20 years? You've been exposed to it for 3 weeks. Okay? I've been exposed to it for 20 years. So something I keep advocating to you is that we're building a toolbox, right? So every problem you solve, you're going to solve in terms of the crap you know how to do. All right? So I know how to do more crap so I can solve maybe more complex problems or solve them maybe in a more efficient way because I have more tools in my toolbox. But I don't have all the tools. It's just like when you have something at the house that you need to fix. You're at the mercy of what you got in the garage. Correct? And typically, guys, it's a screwdriver and duct tape. Okay, I once installed a window unit air conditioner literally using the screwdriver as a support structure. The screwdriver was part of the permanent installation. You would not hire me as a professional. Okay, I'm the nerd guy that just kind of, this works. So what I did is, this air conditioner was in my basement, and I had to chisel out some of the foundation so it would actually fit in this little sub window, because it didn't really fit, it sort of fit. So I used a hammer and the screwdriver to chisel it out, right? Just to break it. And then once I kind of shoved the air conditioner in there, then you have the side things, right? But they're meant for a window, and I had done some structural damage here. So what I did is one side would open fine. It was just kind of meshed over there. But the other one has the accordion thing. So I stretched out the accordion thing, then I shoved the screwdriver in there to hold it open. And then I filled that entire gap with that expanding foam stuff. I didn't look good, but it worked. Professionally installed. And the person who bought the house got that plus a free screwdriver if he chose to dig it out of the foam, because it was encased in the foam, right? Point is, I did all my game playing down there, and sometimes it got hot. I wanted an air conditioner blowing right on me. The quickest way to get in there was with a screwdriver and expanding foam. Done. If you had a real person come in, they probably would have framed it in there, right? So my installation took about 2 hours because chiseling. First, I had to chisel through some metal, then through foundation. I'm teaching a do-it-yourself class next semester if you're interested. But point of that is we tend to solve problems using the tools we have laying around. Sometimes it's not the most efficient problem. Sometimes most efficient solution, but usually we can come up with some sort of solution. Correct? Okay. Last night I was having wings with some students, and all the silverware was in like nice cloth type napkins. I had some gum to spit out, so the solution I used is I took the gum out and I put it in one of the students' hands. I said, "Hey, can you hold this for me?" And people naturally just put their hand out, right? And I put the gum on it and hands off. I used the tools at hand. Oh, yeah.
You told me to swallow it.
That's true. There was a bet that was possibly made that potentially was hazing, but I always make sure I'll take points off his stuff. Okay, so he will always get grades lower than the rest of you. That's a promise. Probably is a pretty legitimate promise. He misses classes, and that's just crap. All right, so in any case, we understand this two-string thing. So every time I give you a problem to solve, I'm asking you to solve that problem in terms of the tools that you've been introduced to in class. Some of you have some tools external to this class because maybe you've done some Java before and stuff like that. I don't necessarily care if you solve problems in a different way, but I would prefer you always solve problems in terms of the tools you have in here because I'm taking you down a very specific path for a reason. Okay? All right, so does this make sense to you? So now, the println method, like I said, has a whole bunch of different versions. There's one that knows how to print out bytes. There's one that knows how to print out shorts. One that knows how to print out floats. One that knows how to print out objects. What is it called when you have a method that has multiple methods with the same name that take a different number and or type of parameters? What's that? What's the crazy word that means that? Polymorphism. Fun word. And when we do our computer science get-together, it's often a quiz question. Could win you an iPod Touch. Huh?
Are we having that anytime soon?
I don't know. That's not my department. I get the email the same time you do. Polymorphism. No, polymorphism, this guy, is when you have the same method with a different number and or type of parameters. Same method name. I mean, you could think of it as overloading, but it's locally overloading. You're not overloading something you got from a parent. So like, for instance, the string. Let me just show you the documentation. Let me show you this too in the documentation. I was just kind of referencing that. I'm a big advocate of learning about the documentation. So the way to get to the documentation for Java is java.sun.com. And this is something left over from years ago because I don't know how to get to the modern one. But this will automatically redirect to Oracle because Sun Microsystems was the inventor of Java. So I'll do java.sun.com. That's the website. And it's going to load this page. Let me make this a little bit bigger. Okay. And we're going to scroll down here under Technologies, and we're going to go to Java SE. That's okay, and that's going to take you to this page. Then over here on the right, under Java Resources, we have something called Java APIs, Abstract Programming Interface. Click on that. And then always just click on the top one. Doesn't really matter. Java doesn't change substantially for the core stuff. So click on Java SE8. It's the current version of Java, current release version. But really any of these is fine. But click on the top one, and that loads the documentation up like this. All right. Now, in every core program, let's go back here real quick. Let me, just for the sake of argument real quick, let me just get rid of random, which then allows me to get rid of that import statement up there. So this is a perfectly working program now, right? Okay. By default, there is one package that's automatically imported into every Java program. And that's something called java.lang.star, which says, give me everything that lives inside the java.lang package. That is the core Java language. Okay, so this line right here is assumed to always be there. You don't have to write it. Okay, and to show you the features of the core Java language, I'm going to go into the documentation. And up here in the top left, you have your packages. And if you scroll down here, we have something called java.lang. I'll click on that. And that shows us all of the stuff inside of java.lang. So the stuff that lives in here is something called interfaces, which we will talk about, but actually maybe not even until 300. It just depends on timing and if we come up with a situation. Then we have a whole bunch of classes. Now we've seen some of these already. We've seen the character class. We haven't seen the character class yet, right? We've seen the string class. Let's scroll down to the string class. Here's the string class. And we're going to be learning about some of the methods here in the string class. But when I clicked on the string class, here is the documentation for it. And we scroll down, there's all this crap in here. What I'm going to teach you is the skill set necessary to use this documentation for any object, not just memorizing strings. You'll be able to go to the documentation if you see somebody says, oh, you have to solve this problem using this particular object. You'll be able to go into the documentation, find that object, and use that object effectively just because you know how to read the documentation. It's not difficult, but it's the skill set to read the documentation. Every class is documented in the same way. Make sense? So just for the sake of argument here, I'm going to go into the system object, which I haven't necessarily introduced, but we've used it. System.out, blah, blah. All right? And we're going to see in here that we have this field up top. Not that important right now, but fields are variables. So I used the example when we talked about objects initially. I said objects can hold 0 or more values and then potentially do more. The potentially do more is the methods, reusable chunks of code. So, for example, the system object happens to have 3 values that it holds, 3 fields. These are variables associated with the object. All right? One of them is standard error, so an error output stream. Another is the input stream, system.in, which we've used for reading in from the keyboard, right? The other one is system.out, which is for writing out to the monitor. The standard output stream is the monitor. So this guy happens to be an object of type print stream. Haven't seen that before, but we've used it. All right, so I'm going to go ahead and click on print stream just for following the documentation here. You don't need to understand all this stuff yet. I'm just kind of showing you the structure. So we're in the system class, so system.out is a print stream. That takes me in here. This is where we'll find the println method. Okay? So we'll find the println method in here because it's system.out.println. So println belongs to the out dude. That is a print stream. That make sense? So I'll scroll down here and we'll see that we have, starting right here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 versions of println. 1 for all of our primitive types, 1 for objects, and then a specialty one for strings. Make sense? So this is called polymorphism, where within a single object we have more than one method with the same name. Every single one of these is called println, but they take a different number and or type of parameter. For instance, this first one takes 0 parameters. The second one takes 1 parameter of type Boolean. This third one takes 1 parameter of type char, 1 parameter type char array, so on and so forth. Okay? That's polymorphism. As opposed to overriding. So let's go back here. I'm going to go, remember we're still in java.lang over here, which is the core Java language that's automatically part of every Java program. So we're going to go to the great-great-granddaddy, object, the generic object that lives in here. So here's object. All right? And we'll scroll down and we're going to find that toString method. So notice that there's not that much to object. This is all the special things an object can do. Okay, it's just the generic stuff that every object has to have access to. Not that important, but we're interested in this guy right here, toString. Returns a string representation of the object. Every single object will have this method guaranteed. And the println method that knows how to print objects relies on that fact. That make sense? Okay? So everything that is an object will have this method. Now, let's go to the random class real quick and see why its toString method prints out the generic. Now, random actually lives in a different package. It doesn't live in java.lang. It lives in something called java.util. It's a utility package. So just real quick, I'll scroll up here and we'll go to java.util. Okay, and down here, just like we had for java.lang, we have a list of classes that are in there. We're going to go down to the random class. And we'll scroll down to its methods. And we see that it never defined a toString method. Now, real quick before I show you what's down right below that, the very top of every object, it shows you its hierarchy. So random has exactly one parent. It has object. So it's one level removed from the original object, okay? As opposed to, let's see if I can give you something else. Scanner, maybe a couple levels. No, scanner's not. String tokenizer, maybe? No. Well, here.
Why does it say that it has methods inherited from class?
That's what I'm about to tell you about. Let me just go to java.io real quick because there's several in there that'll allow me to show you things that are more than one level removed. Oh, I'm in JavaX, that's why it's not making sense. Java.io. So this is where print stream actually lives. So let's go to here, buffered reader. We'll use one of these eventually, but notice that in the hierarchy here, a buffered reader inherits from something called a reader, which inherits from object. Okay? So buffered reader's parent is reader, his grandparent is object. Does that make sense? So if we look at buffered reader and we look at his methods, we see he has no toString method. Well, now let's go to reader. So buffered reader would get everything from its parent reader. So let's see if reader has a toString method. Here's reader. No toString method is defined here. So if we were to create an instance of buffered reader and print it, it would use the generic one. That is objects generic toString method. Every method resolves to its most local definition, just like variables. That make sense? Okay, so going back to java.lang. And the random class. Oh, it's not in java.lang, it's java.util is the random class. I really got to work on my alphabet. Got to practice that. Classes, random. We see that the random class itself, it's always alphabetized, does not define a toString method. Okay? And we see that its parent is object. And we happen to know that object has a toString method. And every class has a reminder of this. So below the method summary, these are methods that are defined specifically by random. And we haven't talked about writing our own methods yet, but we know they exist. We've used them some, so we kind of have an idea on what a method is. I've kind of described it as a reusable chunk of code that does something. We're going to be writing our own methods very shortly, but just kind of know that these are things that do things for us. We get a little section that says methods inherited from object. So we get a summary of stuff that we use that came from our parent. And one of these is toString. Okay? So random's version of toString is actually object's version of toString because it didn't override it. It didn't define its own. As opposed to if we go to java.lang and look at strings, which we're going to be focusing on for the next several classes. So I'll go to java.lang, I'll go down to string. We'll go to the method summary. We see that strings define their own version of toString. Make sense? Now if I scroll all the way up to the top here, notice that string has a single parent, and that's object. So even though object provided a toString method, string overrode that method by writing its own more local copy. So that's what method overriding is. Sometimes they call it method overloading. Another kind of phraseology. I like that word. I'm not sure it's the right word there, but I like that word. So it's not phrasing. Yeah. Okay. So, and if I scroll down to the very bottom here, after the methods, it'll tell us the method's inherited from class object, and notice it's left off toString. Even though that method exists, we didn't inherit it because we overrode it. We have a more local version of that method. That make sense? So kind of get an idea on how this hierarchy thingy works? Okay. So again, reviewing a little bit here. I created two strings, S and S2, both with the new keyword. If I try to compare those guys to each other, using the double equal sign, so we'll say, is S equivalent to S2? Is this a Boolean expression? Who said no? Who thinks yes? Okay, so we have half the class that thinks yes, it's a Boolean expression. So that means the other half the class thinks no? Raise your hand if you think this is not a Boolean expression. Okay, you think it's not a Boolean expression?
Yes.
Okay. What's it? Remind me, what's a Boolean expression?
Any object that boils down to true. Any expression, true or false, that boils down to true or false.
Any expression that boils down to a single value of true or false. Okay, and why isn't this guy a Boolean expression? What's S? Let's resolve these variables. What's S?
Hello.
Okay, S is a string that happens to have the value hello. What's S2? String as well that also happens to have the value hello. So we have two strings, both are hello. What's the double equal sign? Remind me about that guy.
That's the equivalence.
Equivalence operator. So it's one of the Boolean operators, right?
Right.
Okay, so when we test for equivalence, we're seeing is the left side equivalent to the right side, right? So is S the same thing as S2? Is hello equal to S2? Is hello equal to hello?
Yes.
Seemingly we might guess yes,
But it's not.
okay? Or we could guess no. So the result will either be true or false, correct? So is that going to boil down to a single value of true or false? Hello equal hello will ultimately be a true value or it will be a false value, depending on whether or not we were tricked. But at the end of the day, it will still be a single value of true or false. Therefore, that is a Boolean expression. Make sense? Okay? Now, I expected many of you, so you weren't the only stupid one.
I just wanted to learn.
They say.
Yeah, no, that's the point. So only half of you rose your hand. So only half of you were confident. How many of you who rose your hand were just guessing? Yes. Liars. It's not my first rodeo. What 15 years of programming, so I've probably taught, that's over 1,000 students, right? Man. Perhaps this is the first group. You guys catch on right off the bat, right? This will actually be false because the equivalence operator is checking the value of these variables. The actual value stored in S and stored in S2 is a pointer. It's a memory address. That memory address happens to point to those strings. Hello. And another one, hello. Make sense? If we're going to kind of diagram this real quick, because it is important. This is a really important concept. Click more bestest. I love using proper grammar. There we go. Let's go right here. I like drawing too. It's so fun. All right. So we have string S is equal to new string hello. All right. This guy is ultimately going to boil down to memory address. I'll just put a simple memory address, 100. We'll just float that right over the S there. All right. And then I'm going to copy this. Oh, I'm going to get to draw lines on this one too. I love that. So this is, don't judge me. So this is S2, and the new keyword for this guy is actually going to return the memory address 722, except 733 because I missed the 2. All right, so anyways, now we look at memory up here. Man, I shouldn't have made those so far apart, but yeah, whatever. So we'll kind of show a picture of memory up here. So we have that guy, we have that guy, and a whole bunch of empty spots. Then we have these 2 guys. All right? And it just so happens that this guy is at memory address 100. This guy right here. All right, here, we'll shrink this down a little bit. Perfection. And it just so happens that this guy is at memory address 7, I should have done a joke, at 733. All right, so this variable holds the value 100, which is said to point to a place in memory. Make sense? This other guy holds the value 733, which points to a particular place in memory. Now, at that place in memory, we actually have we'll just expand these a little bit for the example. The object. At this place in memory, oops, spelled that kind of crappy. We actually have the object hello. Does that make sense? The object is built at that plot of land. This object is built at this plot of land. The variables hold the pointer, the memory address, where we could follow to get to that value. But the actual value of S is 100. The actual value of S2 is 733. Those 2 guys just happen to point to the actual objects. Make sense? So when we say, we write the Boolean expression, S is equal to S2, these guys are going to resolve to their values. S's value is 100, the memory address 100. S2's value is 733. Is 100 equal to 733? False. That make sense? All right. So when I print out S equal to S2, we get a value of false. Now, if I print out S3 equal to S4, S3 equal hello, S4 equals hello, not using the new keyword, I'm going to get a value of true. Why is that? Let's let me steal that. So we're going to say S3 so this is the other way to define strings using what I refer to as syntactic sugar, right? All right, so I'm going to define these 2 strings. Now what actually ends up happening here is the first time we define S3, first time we define S3, it's going to notice that hello is not stored here. We'll blank these out real quick. It's going to notice that hello is not currently stored in the Java Virtual Machine's special location for literals. So we'll just say that's this version of memory here. So it's going to go ahead and create it. So we're going to go ahead and we'll just use memory address 100 again. So it's going to create hello in memory and store the result. We'll just say it's still at memory address 100. Here, we'll actually change that. It's memory address 213, just so we don't confuse. And here, this is memory address 1024. We're not going to use it, but we'll just change it. That way we are a little clearer here. So the very first time we create the literal hello, it goes ahead and it creates it in memory, in the special literal memory for Java. Nothing different about the memory. It's just a special little block of memory that Java's kind of held to the side to store its literals. And there's a bunch of literals already loaded in there, right? Like 0, 1, 2, 3, 4, 5, our known hard-coded digits. Also letters of the alphabet, those things are literals. But strings, we can't put every word or every sequence of characters you've ever created preloaded in there, right? Because we could just bang on the keyboard and come up with something completely random. So the very first time somebody uses a string, it's loaded as a literal into a temporary literal storage location. Make sense? All right. So the very first time when we defined S3, since we did that before, we defined S4, it noticed, oh, we don't already have the literal hello. So we'll go ahead and create it, and we'll give S3 the memory address. Now, when we define S4 equal to the literal hello, Java notices, oh, we already have that literal defined. So we won't redefine it. It's not at 100, it's at 213. We already have that guy defined. So we'll give you a pointer to where you can find him. Make sense? So now when we say, is S3 equal to S4, we're asking, is 213 the same as 213? Does the value of those variables, which are memory addresses in this case, are they equivalent to each other? Is 213 the same as 213? It is, and that's why we get a true in that case. Make sense? Okay. Third example. What if I try to compare S to S4? It's going to be false. Why is that? We'll use the same slide here. Let me show you the definition of S. So there's S. Now, this guy is not a literal. This guy is specifically asking for new memory. So this disqualifies it from going to the special literal memory location. So what's going to happen is we're going to create a brand new block of memory. So just so happens a new keyword found us a plot of land at 1024. So that'll boil down to 1024. We'll go ahead and have the constructor build us the string hello at 1024. So this guy actually points to this part of memory. So if we ask the question then, is S the same thing as S4? We're asking, is 1024 equal to 213, for example? And it's not. That's why it's false. Kind of make sense? Okay. Now I do that. Oh, go ahead.
So if you're doing string S4 equals hello after you did string S equals new string hello, why wouldn't string S4 find the location where string S equals new string was created?
because since we defined this using the new keyword, we overrode that look for literals default. So we said, find me a new plot of land to build this guy. Don't go and look for literals. Just, I want this to be in a new place. All right? So S was defined first. Doesn't matter if it was defined first or second. Because we used the new keyword, it created brand new memory. When we defined S3 is when the actual hello was created, right? And this is a literal. So because we didn't use the new keyword, Java is going to go to its literal memory bank and say, is there already the literal hello defined in here? And it wasn't when S3 was being defined. Even though S was already defined, which is what you're saying. Hello already lived in memory, okay? But it lived in a random memory location. When we set S3 equal to what looks like a literal, it's a literal value. This is not necessarily different than saying int I equals 5. It just happens to be that string literals need to be created on the fly. At that point, Java said, oh, I don't see it in my literal memory bank, which is let's call it a relatively small chunk of memory relative to your entire bank of memory. So let's go ahead and create it, rather than searching through all 8 gigs of your RAM, looking for a single value. Kind of make sense? All right? So this will be false, because they don't point to the same place. The double equal sign is the primitive equivalence operator. It's built for comparing primitive types. What's a primitive type? Kind of built into the language capable of holding a single value. So the double equal sign works for comparing bytes, shorts, ints, longs, floats, doubles, booleans, chars, and this fictitious pointer that technically doesn't exist in Java because it's everywhere. Okay? So if you have one of those Java textbooks and they talk about pointers not existing, they're actually lying, because everything in Java is actually a pointer. We just don't have a special syntax for it. If we were dealing with C++ or C, we'd have a little asterisk after the variable. If we wanted to create a pointer for an integer, we'd say int star a is equal to 5. Does that make sense? And that would create 5, put it up in memory somewhere, and that would be a pointer to that point of memory. And then if we wanted to see the actual value where that lived, we would put an ampersand before it. I can show this to you real quick, just so you can see the actual syntax for these things. That's weird. Who's Jalowski 6430?
They had Olowski last year on campus.
Yeah, he's in here this year.
Why are they sitting on my terminal? Bugs.
He's a theologian. So
What's up?
he's not a computer scientist. He's a theologian.
Well, chances are I'm probably connected to my server somehow. Whatever. Doesn't matter. There's our homework C. So this is our little C program we created before. So I'll go ahead and create int a equals 5. And then we'll say the value of a is that. The memory address of a is I think it's %p. And let's just do carriage returns here, so it's on 2 separate lines. Okay, so this printed out the value of a. The actual value there is 5. The address that a holds is this memory address. That make sense? Okay, and the reality is let me just add to this a little bit. If we want to define this as a pointer, we'd say int pointer a is equal to 5. Then when we wanted to print out the value of a, we'd print out star a. That is the value at that address. When we wanted to print out, actually in this case I don't think you even need the at sign. If I wanted to print out the memory address, I'd print out the pointer that lives in a. The value of a is actually the memory address. I think this will work. Oh, incompatible integer to pointer conversion. Oh, here, I'll just do it a little different way. Int c is equal to 5. Int star a is equal to the address of c. Now it'll work. Then we're going to print out the value at a, which will be the value at that address, and then we'll print out the actual address of a, which is the value that's stored in a, because a is a pointer primitive type. This is not an int primitive type. This is an int pointer called a, capable of holding a memory address. Make sense? Just to show it to you again real quick, just to walk through the code. So I created an integer named c, set it equal to 5. Then I created another variable named a of type integer pointer. That is a primitive type capable of holding a memory address. And what address did I store in there? I had stored in there the address of variable c, where it lives in memory. Then I wanted to print out the value at a. So the value of a is a decimal, that's this %d, this is a placeholder. And the value is star a, that is the value at a memory address. Follow the pointer to the place it points to and give me that value. The second line here, the memory address of a is %p for pointer, because that's our placeholder, is just a. Why? A variable resolves to its most local definition. A resolves to its definition right here. What kind of value is a? It's an integer pointer. That is, it's a variable capable of holding a memory address. So when I print out a, this will print out the value in a, which should match here, I'll just do it all in one line. Show you how the placeholder stuff works. I'll put a little parenthesis here, then I'll do %p close parenthesis. So we'll do two values. We'll print out the value of a, and we'll also print out the address of c. And those two should be the same value, right? We created our integer c first, stored a 5 in there. Underneath the hood, we know that that 5 has to get stored in memory somewhere. Correct? We know that's a fact. Okay, variables have to get stored in memory. It's just a rule. Okay? So C is going to point to a place in memory, even though we defined it as a primitive type int, not an int pointer. It's still under the hood going to hold the pointer, but by default, C's value will auto-resolve to the integer at that pointer. Okay? So C is equal to 5. Then we set our pointer variable a equal to the address of C. Okay, equal to the address of C. Then we print out the value at a, which is going to print out our 5. That is, follow that pointer, go to that memory address and give us the value there. This next line is going to print out the memory address of a is a. A is a pointer, so it's going to resolve to a memory address, its value. And it should be, I put in parentheses here, %p, the address of C. Those should be the same value, because we built a in terms of C. So the value stored in a, which is a variable capable of holding a memory address, should be the same as the memory address of C, because that's what we put into a. A is equal to the memory address of C. So what's in parentheses should be the same as what's before the parentheses. Make sense? Okay, so now that's looking at a much older language. Nothing we just did there is difficult. And when you actually think about it and kind of plan it out, it all makes sense, right? But it is a little complex, dealing with pointers and non-pointers and all this stuff, right? So Java, being a more modern language, has taken the idea of these pointers, knowing it's important. Okay, and why is it important? It's important for the same, like if we take this down to human terms, if I am inviting you to my house for a party, I give you my address. I don't hand you the house. Houses are heavy. It would be very, very, very memory inefficient for me to hand you a house. Typically, it's very memory efficient for me to hand you a value of anything, a variable. To hand you a string that maybe holds 1,000 characters would be heavy, right? So wouldn't you say that it would almost always make more sense for me to hand you the address where you can find something as opposed to me hand you the value itself? Now there's a couple of exceptions. For example, let's look at the byte primitive type. If on a modern day operating system, it's either 32 or 64 bits. Let's just say it's 64 bits, okay? So a modern operating system, 64 bits, our memory address size is 64 bits. So that means if I hand you a memory address, it weighs 64 bits. If I hand you a byte, the value of a byte, it weighs 8 bits. It's actually more efficient for me to hand you a byte value rather than the memory address where you can find that byte, correct? But not that much more. You could probably lift either of those. It's like me handing you a shoebox versus a shoebox with one shoe in it. You can lift either of them, correct? All right. But if I'm going to choose, let's say I create the house object, and I can choose whether to pass you an address where you can find the house or hand you the house, clearly, in an extreme example, you're way better off handing the address. So you can make the argument that it's never a horrible idea to pass a memory address. At worst, you're just a little memory inefficient if you're actually giving them an address to a byte or a short or an int, and then tie goes to a runner for a long, correct? Long, the value is 64 bits, or the memory address is 64 bits. Pick your poison. All right. Java has decided, why not make these decisions for the user? We just went through the whole, this isn't rocket science, right? If the value is smaller than 64 bits, probably pass by value. Or just choose to pass everything by address and just give up small little memory inefficiencies. Not the biggest deal in the world since we have a lot of memory today, right? Okay? But in older languages like C and C++, the programmer was empowered to make bad decisions. I could choose to create a house object and pass you that house by value. I could choose to do that, and that would never, ever, 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 ever make sense. Is there an example in real life problem solving where it would make more sense for me to hand you my house? Never. Okay, so what Java did is they made some of these decisions for you, because programming languages like C and C++, while being very, very powerful, also enable programmers to get into a lot of trouble by making mistakes. Beginning programmers tend to do that a lot. Now, one of the nice things about C and C++ for advanced programmers is it gives you direct access to memory. So you can write some interesting solutions to problems, some of them legit problems, solutions to problems, some of them like things like viruses, that they can choose to go beyond the bounds of a variable and overwrite other memory. Does that make sense? C gives you direct access to memory. And if you can get to this memory address, you can just do pointer math and get to this memory address. Just add 5 to it. Now I'm overwriting memory 5 slots over. Ha, come get me, right? Java doesn't let you do that on 2 different levels. Java doesn't give you direct access to pointers, and it also has memory living inside of a virtual machine. So it's kind of double levels of protection. Make sense? Okay, so one of the reasons that Java exists is to take some of these problematic features of C and C++ that we can make an argument that are rarely beneficial. Okay, make these features that are rarely beneficial go away so that programmers can focus on the logic they're trying to write rather than having an understanding of pointers. Having said that, clearly, I think pointers are pretty important. Understanding how they work, because this is the infrastructure how computer science works. You know, something Dr. Locklear talks about in his classes is the grand ideas of computer science. Okay, now how many of you are taking more than one class with me this semester? A couple of you are, right? Haven't you noticed in the other classes that we are talking about some concepts that overlap with what we're talking about in the other classes? They're all related. Sometimes we attack it from a different angle, but understanding something in one translates into understanding something in another. And even two topics that are seemingly dissimilar are incredibly similar at the core. So understanding what's under the hood as a computer scientist, because we are professionals in this. Okay, you know, we are race car drivers as opposed to the person who takes their car to the grocery store. Person who takes their car to the grocery store doesn't really need to know about horsepower and how the engine's put together and stuff like that. If you're a race car driver, having some understanding about what's under the hood is significantly more important, right? Okay, so now what I'm about to tell you is sad. If you went out into industry today, most programmers in industry today would not even understand this concept. What's happened is, since technology keeps getting more and more advanced, we forget where we came from. And nobody goes back and teaches that. So I'm a big advocate of understanding what's under the hood. Very, very important stuff. And what it does is it empowers you to be able to really leverage the power of a programming language, because you understand why things work a certain way other than just knowing they do. Kind of make sense? Okay. Real quick, I'm going to teach you one method for strings, and then I'm going to give you a small homework assignment, just so you can keep practicing. So we're going to have the string hello, and there's a method called char at that gives us the character at a particular place in a string. Strings are indexed 0-based. So this H lives at position 0 in that string. The E lives at position 1. The L lives at position 2. The other L lives at position 2. The O lives at, position 2. This is 0, 1, 2, 3, 4. System.out.println s.length is going to give us the number of characters in a string. So the legal positions in this string, and this is important what I'm about to tell you for your homework assignment, the legal positions in this string are 0 to 4. The number of characters in this string is 5. So 0 to length minus 1 are the legal positions in a string. So if I print this out, this is going to display a 5. As opposed to me having a second string, string S2 equal to elephant. If I print out S2's length, this guy knows how long S2 is, which will be 8. So S has a length of 5, S2 has a length of 8. Make sense? System.out.println s.charat0 will give me the H displayed to the screen. S.charat4 will give me the O. S2.charat1 will give me the L. Make sense? What I want you to do for your homework assignment, here I'll leave this stuff up there as an example. I want you to create a string like S, and regardless of what you put in this string, write the code to display the contents of S to the screen one character. Here, let me kick it down a line. One character at a time. So, given S right now, your output should be H, E, L, L, O. Remember, println kicks it down a line. So, print the first character, then print the second character, then print the third character. I'm doing a little loop here, if you notice. All right? Questions about the homework assignment? I will give you this code as a starting point so you can see the example. All right? So I'm asking you to write the appropriate loop right there. All right, I will see everybody on Tuesday.